We are continuing part 3 of the recordings on slide 13. Now, it is possible to solve simultaneous equations using matrices. So, any system of n linear equations in n unknowns can be written in this form. Now, of course, n can represent any number of linear equations, and n here can represent any number of unknowns or variables. So you are only going to be required to solve a system with two linear equations. Now, the system of two linear equations can be written in this form. Now, A is going to represent a matrix that just has coefficients. So you know your coefficient is the number that is next to the variable. K is going to be a vector that consists of your unknowns. So that is what you're wanting to solve for. And then the product of that would be equal to B, and B is going to be a vector as well, consisting of your right-hand sides of the linear equation. Now, A, K, and B are n by n. So this is n by n, meaning rows by columns. And of course, the rows by columns are the same in terms of number here, hence n and n being the same. Then you have n by 1 and n by 1 because you only have a vector in both of these cases for k and for b. So here we are going to solve the simultaneous equations using matrices. So you have your demand and supply, and of course your unknowns for which you're wanting to solve is price and quantity. So we are going to write the system of linear equations, these two, in the form of A times K is equal to B. So remember, A is going to be a matrix. So here is the matrix that just has the coefficients, the numbers in front of or next to these variables. So here we have 10, here we have 1, so you do need to write the number 1. There we have 10p as well. And then here we have minus 1. If there isn't a variable, then you would insert a 0. So you just have your coefficients in this matrix of A. And note, it is a square matrix. It has the same number of rows as it does columns. Then we have our vector K, which has your unknowns. So your first unknown was P, so that is the first one on top. And then your second unknown is Q, so that is the second one at the bottom. And then that is going to be equal to the right-hand sides of these equations, which is these constants. Now, it is very important that before you get it into this form, you in fact rearrange it such that your variables line up. So you need to ensure that your P's line up with each other, your Q's line up with each other, and on the right hand side, you just have your constants. So if it's not in that form, ensure that you rearrange so that the variables line up and the constants. Here again, we have demand and supply equations. They are lined up, our P's and our quantity and our constants on the right hand side on its own. So therefore, I can now take the coefficients of my demand and supply function, and here the coefficient is 1. The coefficient of Q is 2. Then for my supply equation, the coefficient there is 1, and the coefficient here for Q is minus 2. Then my vector, my column vector K, has my unknowns, and my unknowns are P and Q respectively. So you write it in this order. Whichever unknown is first will be on top first, and then you have your second unknown or below that, and that is equal to your right hand side with your constants. Again, we have two more examples. So please see that you attempt these two and that you double check that you are able to write the system of linear equations in this form where you have your product of A and K, a matrix A times K, this vector, and it is equal to a vector with your constants on the right hand side. Now, here we have some home exercises. So please attempt these exercises. The answers are given. You will find the answers uploaded to eCanva in the folder as well. So attempt these home exercises to see that you are on the right track. Right, now the next section is very important. This is what we've been building up towards, and it is matrix inversion. And here we are going to use this particular method to solve for two unknowns. So if you are asked to solve for two unknowns and the method stipulates use matrix inversion, you have to use that method. If you use a different method, you're not displaying that you understand how to do matrix inversion. Now, with matrix inversion, let's say we want to solve for the column vector K, which consisted of those two unknowns. Remember, in the previous example, it was price and quantity. You saw that any system of linear equations can be written in that form: A, K is equal to B. So K in those examples had the unknowns price and quantity from the demand and supply equations that we wanted to solve for, right? So it's always important that you start by writing your system of linear equations in that form so that you have A, that matrix with coefficients, K being the vector of the unknowns, and B being the vector with the constants on the right hand side. So as the name states, matrix inversion, we need to get the inverse of matrix A, which was the matrix that had the coefficients. So if I ask you, what is an inverse or reciprocal? If I asked you to give me the inverse of the number 3, you would tell me that it is 1/3. Also, if you multiply 3 by its reciprocal, 1/3, you would get the answer of 1. Now, in matrices, if you take a matrix and you multiply it by its inverse, what you get is called an identity matrix. Now, for the identity matrix, we're going to use this capital I as the notation, and your identity matrix is like the number 1 in your ordinary arithmetic, and your identity matrix is written with ones written from the main diagonal. Your main diagonal starts in the top left and it goes all the way down to your bottom right. Of course, it can be bigger than a square 2 by 2 matrix. It can be a 3 by 3, 4 by 4. It can be bigger, but this just illustrates that from your top left to bottom right, you would have ones, and the other elements in the matrix would be zeros. So this is your identity matrix. So if you were to multiply matrix A with an identity matrix, what you end up with is matrix A. So in the same way, you take a number and you multiply it by the number 1, what you end up with is itself, right? If I say 3 multiplied by 1, what I end up with is 3. So the same applies to matrices. If you take a matrix and you multiply that by an identity matrix, what you end up with is that matrix itself. So let's see how we're going to go about obtaining the inverse of matrix A. So the first step is to find out the determinant. So this is the notation for your determinant. Now to get your determinant of matrix A, it is obtained by saying AD, taking the elements AD and multiplying it by each other, minus BC, so multiplying the elements BC by each other. So you're saying A times D minus B times C. So just know in terms of your elements, in that matrix A, it would go A, B, C, D. So you'd say AD minus BC, that would give you your determinant. But what is a determinant? What is the point of checking a determinant? Now, the determinant tells us if the inverse of A does exist or not. So if the determinant is not equal to 0, it tells us that the inverse does exist, and we say the matrix is non-singular. The inverse exists. So that is if the determinant is not equal to 0. However, if your determinant is equal to 0, we say that the inverse does not exist and the matrix is singular. But again, what does this all mean? So here we have an example. So if the determinant of matrix A was equal to 0, we would say, number one, that the matrix is singular and the inverse does not exist. But very importantly, here we can see that the functions are linearly dependent. You can see that these are the square of those two coefficients. So there's linear dependence between these two examples. So if the determinant is equal to 0, we will find that either the system of linear equations does not possess some unique solution. So there could be a situation where there's infinitely many solutions or no solution at all. And that is what it means if the determinant is equal to 0. Now let's see how we would get the inverse of matrix A. So this is the notation to represent that this is the inverse of that matrix A. And it is given by 1 over the determinant multiplied by, so this becomes a scalar, multiplied by, here we've swapped the elements A and D with each other. So you swap their position and you change the sign of elements B and C. So this multiplied by the scalar 1 over the determinant would give you your inverse of matrix A. Now you can see why the determinant could not be 0 because you cannot divide by 0. Now take note that if you take the inverse multiplied by matrix A, what you end up with is an identity matrix. Or if you have matrix A multiplied by its inverse, you end up with an identity matrix. In the same way, if you take a number and you multiply it by its inverse, 3 multiplied by a third would give you the number 1. Now that you have the inverse, the final step is to solve for your unknowns. Now, in your case, you will only do 2 by 2 matrix inversion, but in honors level, you may be exposed to 3 by 3 matrix inversion, as well as other methods to solve for a system of equations. So once you've expressed your equations in this matrix form, A, the product of A and K is equal to B, where A was that matrix of your coefficients, and K was the vector of unknowns, and B was the right-hand side. Now, if you multiply both sides by the inverse, you apply that to both sides, you would get this step. By the associative property, I can group the inverse and matrix A, and I know that would give me my identity matrix by the definition of an inverse. So now I have my identity matrix times K is equal to my inverse times B. And of course, the identity matrix is just like the number 1. So therefore, I can just write it as K, which was the vector of unknowns, is equal to my inverse times B, which is the vector with the constants on the right-hand side. And this is how you would go about solving for the vector with your unknowns. The following couple of slides goes through worked examples. So I will go through the worked examples in the next video.